Morning, everyone. So today, phase transitions 2. And what we're going to do is have a look at the 3D EFT that we found last time. Let me just grab this around. Find the phase diagram. And then we'll look at the electroweak case as well, which is not so different. So last time we found this effective field theory for our abelian Higgs model, and it had a phase diagram. I didn't actually draw this phase diagram last time, but we kind of saw it. So there were two parameters in the potential that turned up, and lambda 3, which was the coupling, stayed positive the whole time, and m3 squared went from positive to negative as the universe cooled, or whatever, as the temperature decreased. And so we get a line of second order transitions. Which separates our broken phase up here. Nope, sorry, our symmetric phase up here, wrong way around, from our broken phase down here. So quite a simple phase diagram. Even more simple than the ones we saw for like helium and QCD and stuff. But yeah, I'm going to look at today why this isn't the end of the story. And one of the things to pick up and to start with is our 3D EFT, and we chatted about this in the exercises, is super renormalizable. Which means it's essentially insensitive to the ultraviolet. Couplings don't run, essentially, but it's sensitive to the infrared. So the next question is, okay, it's sensitive to the infrared. What happens then if a mass goes through 0? When the mass goes through 0, we have something very infrared happening. So our super renormalizable theory is going to be super sensitive around there. And that's the bit that we care about. That's where the phase transition happens. So yeah, what happens? As m3 squared goes through 0. To kind of try to understand this, we'll look at what you might look at in a renormalizable theory or something like that. You might look at how the coupling runs. And like as we change the RG scale, as we add in loops, how does the coupling run? So if we start with this diagram, which is just, we know from our, and add the one loop corrections to this. So add the one loop corrections to a 4-point interaction or a 4-point scattering. And let's choose the external momenta 0 for all the external momenta. And then we have the 3 different possible diagrams. and then the U channel, which is always more difficult to draw. With arrows appropriately. And then let's just drop the gauge stuff for a second. Oops. And we can just apply our Feynman rules. This first one is minus 4 times lambda 3. For each of these vertices, we get 4 times lambda 3. So we get that squared. If I put the arrows in, you can see that this one has a symmetry factor half, and the other ones have symmetry factors 1. So that's the sum of those 3 diagrams. And then we get the same loop integral for each. In principle, higher order terms. Here, I'm not matching an effective field theory. I'm doing a calculation within the effective field theory. You'll notice I don't have sum integrals anymore. This is my pure 3D theory. So this is the infrared modes interacting with themselves and not the non-zero Matsubaira modes, which are all incorporated in these parameters here. So I'm not going to do a UV expansion here. I have to actually do this integral because now I care about the infrared. I'm doing an infrared calculation. And if I do this integral, I find the following. So I can pull out an overall factor of 4 minus 4 lambda 3, and then I get 1 minus, this gives me a 5 over 2, and then I can do this integral and I get 5 times lambda 3 divided by 4 pi m3 plus higher loops. So what does that tell us? It tells us that the 4-point interaction is corrected at one loop by this kind of a diagram. Did you have a question?
Yeah, should we square the integral to propagate them? Or?
Yes, it should be squared, sorry. Thanks for catching that. So what have we learned? We've learned that the 4-point interaction is corrected at one loop by this kind of a term. And it's lambda 3 divided by m3. So this is different than you would get in 4D. And the difference is because lambda 3 now has positive mass dimension 1, and so does the mass. So we need this ratio to get a dimensionless combination. And in principle, if I were to do a 2-loop calculation, I would just find something order lambda 3 squared on 4 pi squared m3 squared. And for each loop, I'm just going to get this factor again with this ratio of couplings to masses. So what I find is that lambda 3 on 4 pi m3 is the dimensionless expansion parameter. Within the EFT. Okay, maybe you can start to see problems with I'm going to go through M3 0. But let's have a little bit of a think. So imagine I'm not at TC. So we had some expression for M3. M3 squared is equal to minus mu squared plus, what was it, lambda on 3 plus g squared on 4? T squared, something like that. This is what we calculated last time. Now, if you imagine we're at arbitrarily high temperatures, and here I've dropped the gauge coupling for simplicity, but the same story would apply if I'd included it. So let's say we just have this lambda term. So at high temperatures, this goes like lambda times t squared. That's what happens up here above TC. And if I go through TC some like order 1 amount below it, so let's say I'm at half TC. If I'm at half TC, then there's no special cancellation between these, and again, the order of this term should give me the order of lambda 3, so the size of lambda 3 should still be of order lambda t squared. So for all of above and down to a bit below, the size of m3 squared is lambda t squared. And the only place where that breaks down is when these two cancel against each other. So this is of order lambda t squared when t not very near Tc. And what does that tell us for our expansion parameter? So we get lambda 3 on 4 pi m3 is like, so lambda 3 goes like lambda times the temperature, just from the kind of scaling that we worked out from last time, and then 4 pi, and then square root of lambda t squared. So this goes like square root of lambda over 4 pi. So this is my loop expansion parameter within the EFT, away from TC. And you'll note that this is smaller than my usual loop expansion parameter at 0 temperature, which would be lambda divided by 4 pi squared. So it's kind of the square root of the usual loop expansion parameter, which means the loop expansion within the EFT is converging slower than you might expect from 0 temperature physics. Yeah, we typically call this scale, let me just give you some terminology. So the non-zero Matsubaru modes live at the hard scale. The soft scale is what we're looking at right now. You can also write this as g times t, square root of g squared. And then imagine I were to go all the way down to the scale where this expansion parameter is order 1. At that point, the mass goes like lambda times t. So then there's some ultra soft scale which is lambda times t, or g squared times t in the gauge case, and this one is non-perturbative. So if I think about my potential, so the potential for my 3D EFT. So at temperatures above TC, temperatures below TC, I have a small expansion parameter, as long as my coupling is sufficiently small. But if I look at the temperature of TC, where the mass is 0, my expansion parameter is either, it's at least 1. In some sense, it goes through infinity. So this line here is really unknown. So that's somehow non-perturbative. Like my prediction for that line is not a good prediction, whereas the predictions for these lines are okay. So unfortunately, we just don't know the answer in this interesting region where something happens. We know after the transition we're over here, and before the transition we're up here, but during the transition, it's non-perturbative, because it goes through this ultra-soft scale. So, yeah. So, which means that if we go back to this picture from the beginning, we actually don't know what happens around here. Even though this is the leading order prediction, really anything could happen because of our expansion. because we have non-perturbative physics. Put on the timer. Let me do that again. So to make progress, let's consider the effective potential within our EFT. And to do that, we need to expand around a background field. So expand our phi is 1 over root 2 background field plus Higgs field plus I times Goldstone. This is the usual kind of expansion from electric theory. And if we look at our Lagrangian and have a look at, let's just have a quick look at how the Higgs mechanism works out here. So in our EFT Lagrangian, we have the term di phi star di phi. And in that, we then have the term, I'm looking for the mass term for the gauge field. So I'm going to get 2 powers of 1 over square root of 2. I'm going to get 2 couplings, 3D gauge couplings. I'm going to get 2 powers of phi squared, and then I'm going to get AI. So we have a Higgs mechanism as we'd expect, and our vector mass is G3 squared phi bar squared. If we were to do the analysis for the other degrees of freedom, we'd find that the A naught field gets a correction to its mass by the coupling with the Higgs. The Higgs itself gets a mass, correction from the background field. There's a 3 there. And then the Goldstone gets a mass, correction. Like that. So that's our mass spectrum. This is our model. And when any of these masses go through 0, we potentially have trouble with non-perturbativity. So we want to understand these different degrees of freedom, how they back react on the condensate, and when we compute this effective potential, what the effects of these particles are. And yeah. So for simplicity, I'm just going to write psi A is the collection of all the fluctuating degrees of freedom. So we have the Higgs, the Goldstone, the A naught field, and the AI field. And we'd like to include these particles and how they contribute to the effective potential to try to better understand this yellow region here. This is the effective potential in 3D, so this factor of beta, or 1 over temperature, has been absorbed into the normalization of the field. So this has the effective potential now has mass dimension 3 instead of 4. So this is the integral over non-zero modes of all of my fluctuating degrees of freedom. The action evaluated on the background, and then quadratic fluctuations around that. Ooh, that's going to be, okay. plus higher order. So what I've done here is I've expanded the action around the background field phi bar. So the action is background plus fluctuations at quadratic order plus higher orders. The linear order cancels, essentially because the linear order always involves a zero momentum mode. These tadpoles have to have zero momentum going through them, so if I restrict that, then I can get rid of that. Then I have a kind of a background part, which will be my background tree-level potential, and then I have these kind of loop corrections to that. And I can, this background part doesn't depend on the fluctuation, so I can pull it out. It also doesn't depend on, it's just equal to space-time volume times my tree-level potential in my EFT. That's this first term. And then the second term is a Gaussian integral. And I can do Gaussian integrals. I just get a determinant of the thing in the middle, this matrix here. Just the second derivative of the action. I'm going to get a determinant of that. So I get determinant of delta squared S of t, delta psi A, delta psi B, to the minus a half. And that's just from the Gaussian integrals there. And then in principle, 1 plus higher order. And I can rearrange that now for my effective potential and write that my effective potential is my tree level potential. I've just taken a logarithm of both sides, plus 1 over 2 times the volume of the trace of the log of this operator. Plus higher order. And I have trace log because here I have determinant. Then I take the logarithm of that, so I get log det, and log det is trace log. Okay, so this is how fluctuations affect my potential, and I want to know how they will affect things, especially in this region in the middle here. And what I need to do is calculate the trace of the logarithm of this operator, which is the second derivative operator. So I need to find the eigenvalues of that operator. For scalars, this is fairly straightforward. If I expand my EFT and look at the terms quadratic in the scalars, for example, I have one that looks like this in Fourier space. These are 3D P's and Q's. I get a half. I have a Higgs term. So it looks like this. So this is just rewriting in Fourier space the Higgs quadratic term. And this is the relevant eigenvalue I then need to pull out. Of this operator, p squared plus m squared. So when I'm taking this trace of the log, I'm going to get logs of p squared plus m squareds. For the gauge fields, it's a little bit more difficult for the vectors. AI, we have the following. Instead of p squared plus m squared, if we expand out the action, we get the following. Mij for AI aj is, so from the usual kinetic term, I get p squared delta ij minus pi pj. Then for my gauge fixing term, I have 1 over psi 3 pi pj. And then I have this Higgsing mass term, mv squared delta ij. Maybe you can kind of see in your head where these terms come from. So this is my f squared. This comes from di ai squared, or yeah. And then this term comes from that mass term that we looked at here. Okay, so it's a little bit more difficult than that. We now have a matrix. This is a 3 by 3 matrix, because I goes over 1, 2, 3. So yeah, sorry. This is from Fij, Fij. This is from gauge fixing, and this is from Higgs mechanism. Any questions at this point? Okay, yeah. There is no zero mode here.
No, because you have excluded it from the...
Oh, you mean this one here? Yeah, yeah, exactly. So in order to proceed with this determinant, a helpful thing to do is to recognize that we have some projection operators. There's a transverse projection operator, which is delta ij minus pi pj on p squared. And there's a longitudinal projection operator, which is pi pj on p squared. And the sum of these two projection operators is 1. So writing my m in matrix notation, then I have the first term is just p squared times the transverse projection operator. And the second term is 1 over psi times p squared times the longitudinal projection operator. Yeah. Sorry, this is, yeah, maybe this is non-standard. This just means a matrix. So I guess I could have written PT ij. Yeah. And then finally we have mv squared times the identity, which is the sum of the transverse and the longitudinal projection operators. Which allows me to then, I can then split up the PT and the PL bits, and we get P squared plus MV squared in the transverse direction plus 1 over psi times P squared plus MV squared in the longitudinal direction. And these matrices, being projection operators, must have eigenvalues either 0 or 1. Because if you square them, they give themselves back, and the only way you can do that is if you have eigenvalues 0 or 1. And this one has 2 eigenvalues, 1 and 1, 0, and this one has one eigenvalue 1 and 2, 0. So we can now put it all together. We now know essentially the eigenvalues and the one loop part of the effective potential within my EFT is, I'll write down the scalars, a half times log q squared plus m Higgs squared plus a half times the integral over log q squared plus m Goldstone squared plus a half times the integral over log of q squared plus the A naught field's mass. And now come the gauge fields. The multiplicity of this eigenmode is 2. There are 2 of them. So we just straightforwardly get to 2. And then we have q squared plus mv squared. And then there's only one of these. So we're going to get a half q log of 1 over psi q squared plus mv squared. And in the end, we're going to want to take psi to 0 from above. That was our gauge choice. Now we have the same loop integral over and over again. This loop integral you can do by somewhat standard means. And we find that it's minus the 12th pi times this mass squared to the 3/2. So we get mh squared to 3/2 plus mg squared to 3/2 plus ml squared to 3/2 plus 2 times and then we come to this last term. So if I take this, I can do this integral in a couple of ways, but there's a 1 over psi for the first term. What I can do is I can rewrite this as log of 1 over psi plus log of q squared plus psi mv squared. Log of 1 over psi is field independent, so I don't care about it. I'll drop it. And then the second term is log of q squared plus psi mv squared. Then I take psi to 0. I'll get, psi times mv squared. I take psi to 0. At the end, I'm going to get 0. So this last term gives me 0. I guess I can write psi times mv squared to the 3/2. And this one's going to give me 0. And then in principle, plus a field independent bit, but which I dropped. Okay, so that's how things change. It's already a little bit complicated. So I'll simplify again to the case where the gauge coupling is 0, and I'm just going to get the scalar parts. And we'll have a little bit of a closer look at that. So for the pure scalar theory, our effective potential then is a half m3 squared phi bar squared plus a quarter lambda 3 phi bar to the 4. So this is just the tree level part minus a 12th pi m3 squared plus the Higgs mass to 3/2 plus the Goldstone. So this is just the pure scalar one, just to kind of look a little bit more in depth at that. So one thing that immediately pops up is we have a branch cut over here. If you consider we're in the broken phase, so m3 squared is negative, then because this is negative, the whole thing can be negative. So this part is positive definite, this part is positive definite, but the mass can be of either sign. The mass squared can be either sign. So when this is negative, the whole thing can then be of either sign if phi bar squared is small enough. So this thing can give me a negative number to the 3/2. And I can take that either above or below the branch cut and I get a different answer, right? A different imaginary answer. So if I were to draw on the plane of phi bar squared, this is the real part of phi bar squared and this is the imaginary part of phi bar squared. If I were to draw the effective potential, I'll find that there's a branch cut at minus m3 squared on lambda 3. What that means is that my effective potential is just not defined there. Another way to think about that is, at those points, we have a mode with a tachyonic mass, has a negative mass squared. And I'm asking for the correction from fluctuations in the tachyonic direction to the background energy. And this just isn't a good question to ask. If I have a potential which looks like this, and I take and I start at the top, and then I ask, what's the contribution to the energy of fluctuations around that maximum? I'll find that I don't get small fluctuations, and I won't get a sensible answer. And that's exactly what's happening here. When I'm on this branch cut, I'm asking for fluctuations which do this, small fluctuations around the top of the hill. And you just don't have small fluctuations around the top of the hill. You have big fluctuations around the top of the hill, and that's why it all breaks down. So I'm asking the wrong question. It's okay, though, if I'm around a minimum in both cases. When both of these are positive, then there's in some sense a legitimate question to ask. What is this quantity? Yeah. If we're deep in the broken phase or deep in the symmetric phase, we find, though, that this gives a small correction to the leading order. So when I do beforehand, there was this yellow band in the region near the phase transition where everything breaks down. Then this gives a large correction. But if we're very, very far in the symmetric phase, or basically if we're far from TC, then this is a small thing. Or in general, we find that that the one loop bit divided by the tree level bit is, roughly speaking, like this. And we can arrange things such that our potential looks rather different from before. One can find a situation where the potential looks like this, and it looks like you have two minima. So we have a kind of rather different setup than before, potentially a first order phase transition. But to get something like this, you find that you need this to be about 1. So the effective, so this thing here either doesn't do anything interesting away from the critical temperature, or it does something interesting, but when it does something interesting, my expansion parameter is 1. So this is kind of consistent with what we found before. We have strong coupling near the phase transition where the mass gets small. Then the potential looks really different to how we found it before, but the expansion parameter is 1, so we can't trust this. So the previous result was like that, let's say, and now the result's this. And they look rather different from each other, but neither of them are correct, unfortunately, because we can't trust perturbation theory. Yeah. So why do things go wrong in our case? They go wrong near the critical temperature, where the combination of these two terms is much smaller than either term separately. Let's write it like this. But when we have this looks like a scale hierarchy, right? In fact, we have some things which have masses of order g squared, t squared. We calculated one yesterday. The A0 field has a Debye mass of this size. So what went wrong is there's a new scale hierarchy. And what we find is that the Higgs and the Goldstone boson are much lighter than the different components of the Debye field in the broken phase, sorry, of the vector field. But this is okay, we just have a new scale hierarchy. We kind of know what to do when we have a scale hierarchy. We did that before. We integrate out the heavy fields. Here, when I did this computation, this is in some sense integrating out the scalars, which are the light fields. So that's when everything breaks. But if I integrate out the heavy fields, then I should be able to make an effective field theory for the light fields. Yeah. This scale hierarchy implies another hierarchy because so the Higgs mass is like lambda 3 phi bar squared, and this is much less than the vector mass, which is like g3 squared. Oops. Which is like g3 squared phi bar squared. And if you combine these two things, that the Higgs is much less than the vector, you can see that the phi bar squareds cancel, or can be pulled out, and we just get that lambda 3 is much, much less than g3 squared. Or, because these both have factors of t, in terms of the zero temperature couplings, lambda is much less than g squared. Let's stop there for a 5-minute break. Okay? So I just rubbed it off, but the last thing I said was we have a new scale hierarchy. And the new scale hierarchy was that the vector field is heavy compared to the scalar field. So to proceed, we want to integrate out the heavy field, which is the vector field. And in terms of the effective potential, we can do that by including the loops of the vector field, but not the loops of the scalar field. So we want to integrate out AI. I'm just going to drop A naught for simplicity. You can include A naught, but either there are two ways that we can include it, both of which require an extra 5 minutes, but give us no extra insight. So I'm just going to drop A naught contributions. So now we want to get the we want to approximate, we want the tree level potential of the new effective field theory. Our full effective potential is approximately the tree level potential of the new effective field theory. And that's with the newly discovered heavy degrees of freedom, the gauge fields integrated out. And as before, we get the same terms here. So for writing these quite so many times. But then we also get this minus 12 pi times 2 times G3 squared, phi bar squared, to the 3/2. And that's the contribution from integrating out the heavy vector field. And this we can write as, let's write the whole thing. It's minus 1 over 6 pi times G3 cubed, this is always positive, times the modulus of phi bar cubed. And this is, we just have three terms here. We have phi squared, phi to the 4, and minus phi cubed, or modulus of phi cubed. And our potential looks rather different from how it did before, around the critical temperature. One finds this kind of a potential with two minima. And you can find the positions of these minima by solving v dashed phi bar equals 0. And then you can solve for the special condition where the two minima have the same height by simultaneously, let's call this phi bar min, solving for v min minus v of 0 is 0. Okay. This one actually is 0, so yeah. By solving those two equations simultaneously, you can find, you get this kind of a potential. And this gives you a position here, phi c is G3 cubed on 3 pi lambda 3. And this happens, this special condition where the two minima are the same, happens when the mass is related to the couplings by the following. The mass is equal to, I'll just write it like this. That looks right. And this is just now a kind of simple polynomial equation that we can solve. And we've solved it, and I've just written the answers there. And you get this kind of a potential at this value of the mass, and at larger values of the mass, we get potentials like this, and at lower values of the mass, we get potentials like this, and eventually like that, and eventually like this. So we have all of these in between. And this is our critical temperature here. So great, we've got a different answer from before. This is a first order phase transition, by the way, because we have two minima coexisting at the same temperature. Phase transition. So we have a different answer, but we had a different answer before. Can we trust this answer? What about perturbation theory? Now, one reason why one might think that we could potentially do better here is around the phase transition, masses never go through zero. The scalar always lives in one of these minima, and the mass never goes through zero in the minimum. So that helps. So we're never going to go through zero and then have that zero on the bottom of our expansion parameter. The other thing which is going to help is that we have this scale hierarchy. So as I said before in yesterday's lecture, in order to have a perturbative phase transition, we need a scale hierarchy. We found a non-perturbative phase transition when we didn't have a scale hierarchy, when we just had the pure scalar theory, which doesn't have a scale hierarchy. And now we have the vector field in there too. We have a scale hierarchy, and that allows us to have a perturbative phase transition. We needed that. So let's have a look. We find that if we add further scalar loops, we get, as expected, lambda 3 on some pi times the Higgs mass. But the Higgs mass is, roughly speaking, square root of lambda 3 5r squared. And if I'm now going to evaluate this at the critical temperature to ask, well, this is where we expect it to be worst. Evaluate it at the critical temperature. I can then put in my computed critical phi and then my computed critical Higgs mass. And I get that it's equal to lambda 3 on G3 squared to the 3/2. And if I were to do the same for vector loops, where we get the coupling divided by the mass, and I again take my mass from G3 times phi, I'll get that this is equal to lambda 3 on G3 squared, or 1. But what is lambda 3 on G3 squared? So both corrections are controlled by lambda 3 on G3 squared. But this is m Higgs squared on mv squared. And I said before, we have a scale hierarchy, where the vector is much heavier than the Higgs. So if we have a scale hierarchy, that's small. Which means that the scale hierarchy gives us a perturbative phase transition, where we can understand what's going on. And if we didn't have a scale hierarchy, we wouldn't have a perturbative phase transition, and we wouldn't be able to understand what's going on. So we can now make a better guess of the phase diagram. And it turns out that this is the important parameter to plot things with respect to, and this is roughly speaking lambda on g squared. And on the y-axis I want some kind of temperature variable, something that changes with temperature. So I'll choose this, because the mass is the main thing that if I scale out the T from the couplings, the mass is the only thing that's going to go through zero and change with temperature. Then before I had a line of first order phase transitions where the mass went through zero, sorry, second order. Before I had this at leading order. But now I have a line of first order phase transitions at positive mass. And this positive mass is proportional to G3 squared on lambda 3. Yeah. So it's proportional to 1 over this, which means we get a line of first order phase transitions which looks like this. And we have the symmetric up here, and we have the broken down here. And in the symmetric we have a massless vector. And here we have a heavy. But at some point, we're going to hit lambda 3 on g squared is about 1. And once we do that, we no longer have a scale hierarchy and everything breaks down. So we have another here be dragons. But we've made good progress. We actually trust the existence of this line now, because we found it within perturbation theory and we were able to show that perturbation theory works at this point. So this line continues in some unknown way into the strong coupling region, but in the weak coupling region over here, we know exactly what's going on. This story actually evolved over decades of study. And it required a bit more to work out what happened in the Hebe Dragons region, which I'll try to chat about quickly now. How am I doing? Okay. So ideally, if we want to understand what's happening at the end of this line of first order phase transitions, so let me just say that it's first order. What's happening as we go this way, it would be good if we can find out what's happening at this point and this point and this point, like. But here it's perturbative, so we know what's happening. So if we start from the perturbative region and ask how things change, one thing we can ask about is the latent heat. This is how much heat is kicked out at the phase transition. And the dimensionless version, because it has dimensions of mass to the 4, can be evaluated like this. F broken minus F symmetric on T to the 4. Evaluated at TC. Oops. So this is the latent heat. This is the jump in the first derivative of the free energy as we go through the transition. But this quantity here, we can also write in terms of our effective potential evaluated at the minimum. This thing is basically our 3D effective potential evaluated at the minimum on T cubed because of the mass dimension difference in 3D and 4D. So we want the logarithmic temperature derivative of effective potential evaluated at the minimum, which depends on m3 squared, lambda 3, and g3 squared. I'm going to continue to drop the A0 field, again, just for simplicity, evaluated at Tc. And we know the potential now, so we can go ahead and evaluate this. And we can do so by chain rule, one of those rules, the derivative rule. And we'll get the following. So d phi bar min Tc plus the derivative with respect to the mass, and then the temperature derivative of the mass plus other terms. Now this term is 0 because it's a minimum. And the structure of this term is somewhat interesting. This object here is pure 3D. If we know the effective potential within the 3D theory and its dependence on 3D parameters, then we know this object. This thing depends on dimensional reduction. So this is 4D/3D. This depends on the interaction of 4D and 3D. So the terms in the latent heat factorize into a product of something which is purely 3D and then something which is to do with the matching relations. And let's just focus on this pure 3D bit, because that's what we've been doing. This one's kind of easy. We've already worked this one out, basically. This one, this pure 3D bit, what is this? What is this? This is evaluated at the minimum. So I can write this as minus 1 over volume log. So why have I done that? By the way, this is evaluated at the minimum. So this argument is no longer free. We've essentially integrated over it, which is why I don't have a p not equal to 0 there. Well, I can take this derivative inside and get an interesting relation. So I get 1 over volume outside. This thing is the partition function, so I'm going to get a 1 over z when I take the derivative of the log of the partition function. And then I'm going to get d phi dA ds of eft by dm3 squared e to the minus s eft. And this is just a derivative with respect to a parameter. This is an easy derivative to take. And I'm just going to get the integral over x of phi squared, or half phi squared. Or sorry, I guess phi star, let's write it like that, phi star phi. But then I'm going to divide by volume. I have a 1 over z. This is just an expectation value. Can you see that this whole thing is just an expectation value? So the answer is just the expectation value of phi star phi, volume averaged. This is my vol average, and this is my thermal field theory average. So now I can now write my latent heat as something which is kind of easy to evaluate. This thing was easy, times that. And this is, in perturbation theory, just a half times phi squared. Sorry, phi bar squared, which we've evaluated. So it's 0 in the symmetric phase. And what is it in the broken phase? G3 to the 6 on 18 pi squared lambda 3 squared in the broken phase. And my latent heat is proportional to this quantity. So the latent heat divided by Tc to the 4 is proportional to, so lambda is proportional to the Higgs mass squared and G3 the vector. So this is again that ratio of masses turning up again. So that means my latent heat, if I just take that part, is proportional to m vector squared over n Higgs squared. So it's, yeah. So as the hierarchy of scales grows, as my vector gets heavier compared to my Higgs, this gets stronger as it gets more perturbative. And consequently, it gets weaker as it gets more non-perturbative. So going back to this phase diagram, the transition is super strong up here and gets weaker and weaker as we go down here. So the expectation for what happens is the following. It's getting weaker and weaker. So it's expected to just end at some point. And the reason this can happen is because we don't have a global symmetry breaking, because the order parameter is not, even though in perturbation theory it seemed like the relevant quantity was phi bar, when we look at physical things like the latent heat, it's actually phi star phi which turns up, and not phi bar itself. So although this turned up in gauge-fixed perturbation theory, this is really the physical thing that turns up. And this thing, although it's 0 in perturbation theory at leading order, it's not 0 at higher orders. This thing includes fluctuations. Before renormalization, it's positive definite. So if I include fluctuations, this will be positive. So it's just not 0. Okay, I can renormalize it and change the value, but 0 is not a special point. So there's not a symmetry breaking, as I argued before. Elitz's theorem tells us that gauge symmetries are never broken, which is why this line of first order phase transitions can end. And then over here, you can go between the symmetric and the broken phases without crossing a transition. So it depends then on the value of lambda over g squared in your model. Is there a question? Yeah? Yeah, it's a critical point. Cool. So before I put that, so stuff that definitely breaks down at when lambda over g squared is order 1, but there is a special point, let's call it x star, which allows us to distinguish what phase transition will happen. So let's say you're given a model, you're given the abelian Higgs model, and someone tells you the parameters, an experimentalist or whomever tells you the parameters. If you want to know, is the transition second order, is it first order, is it a crossover, you just need to look at lambda over g squared, and if it is, how do I write this? Let's write it like this. The order of the phase transition, if lambda on g squared is less than x star, then it's first order. Lambda on g squared equals x star, second order. And if lambda on g squared is greater than x star, it's a crossover. We weren't able to compute this x star. That's because the x star happens as the thing gets more non-perturbative. It also gets weaker, but because it gets more non-perturbative, at this x star point is a point we actually can't compute in perturbation theory. So for the electroweak theory, the story is the same. It's identical. In the electroweak theory, it's the SU2 field that matters for the gauge coupling. The U1 field, the hypercharged field, is not very important, but the Higgs matters. So the relevant quantity in the electroweak theory is lambda 3 for the electroweak Higgs, the actual Higgs, divided by G3 squared for the weak gauge group. And this is just approximately lambda Higgs divided by G squared weak. And people have studied the electroweak theory on the lattice using effective field theory. So they did all the integrating out that we did, and then they studied the simple 3D effective theory on the lattice. Because the only thing that became non-perturbative were these infrared 3D modes. So dimensional reduction still works fine. So you could do dimensional reduction, be left with these non-perturbative 3D modes, and then put those non-perturbative 3D modes on the lattice. And then you can work out what x star is. And x star electroweak turns out to be surprisingly small, about 1,1. And in the electroweak theory, lambda Higgs on g weak squared is about 0.3. And you can see 0.3 is bigger than 0.11, which means we're in this crossover region. Just draw a couple of plots of what it looks like in the actual electroweak theory. So this quantity which we looked at, phi dagger phi, volume averaged, you can divide by the temperature. You can also compute on the lattice. This is a nice gauge invariant observable. It's very easy to compute on the lattice. And if you do so, you get the following plot. At high temperatures, you get some value. After renormalization, it can be positive or negative. In the renormalization choice that they chose, it was negative. So it's like this for a bit, then it does this. This is roughly 160 GV. There's no jump. It's smooth, but everything kind of happens. This is, that's a 1 GV range, let's say. So everything kind of happens within 1 GV, but nothing diverges. If we also plot the susceptibility, so we plot phi dagger phi squared minus phi dagger phi all squared if we plot the susceptibility, we find that this thing has a peak at again at 160 GV, telling us that something is happening at 160 GV, but there are no discontinuities. It's a crossover. Yeah, that's all I had to say. Thanks.
So, for this entire thing, we assume that the couplings are constant, which isn't entirely true because you can define beta functions and the couplings will then be running. So, I don't know, how do you sort of do this analysis if you want to consider the case where, in general, there could be running of couplings, right?
So the question was, what happens when we include running of couplings? So running of couplings and beta functions is a higher order effect. If you want to include that, you need to do everything else to higher order too. If to include the running of couplings, you need to do dimensional reduction to the next order, which actually involves 2 loop diagrams. And the reason is because they're enhanced by this power of t squared. Unlike at 0 temperature, where you can get renormalization group invariance all at 1 loop, at high temperatures you have to mix the loop orders to get RG invariance because of t squared enhancements. But if you do that, you can get RG invariance. The story is the same as I just presented. You just need to work harder. You get more precision, of course, and that's important. And was needed really to nail these kind of things down because a lot of couplings in the standard model are order 1. The top Yukawa is important here, it's order 1. But divided by 4 pi, it's not. So yeah, you can do it, it's just a bit more work. What is happening? Yeah. So the masses of particles suddenly become dependent on the Higgs. That much happens. It's difficult to say stuff if we want to be gauge invariant in how we're saying stuff. Like the normal story about the Higgs mechanism just doesn't apply. So you could say, okay, stuff is getting a mass, but actually everything has a thermal mass anyway. So everything has a mass here, everything has a mass there, apart from the AI parts of the photon. Everything is massive everywhere, but the dependence of the mass on the other parameters changes. So it only becomes dependent on the Higgs here. It doesn't depend on the Higgs here. It's just thermal masses here, and then suddenly the mass of all these particles starts to depend on the Higgs. That's I don't know, that would be a way of describing it.
Wait, would the W and Z also have a mass in the thermal regime?
Yeah, I mean, W0 and Z0 certainly have a mass, but then also, because they're non-abelian, even the spatial components get a mass. I didn't talk about this, but the spatial components also get a mass, just non-perturbatively. If you put them on a lattice, you just have a massive theory full of massive degrees of freedom. Yeah.
So what are we learning from the second graph here compared to the first one? So how are we to interpret this peak?
So this first one, you might think, okay, maybe there's a little jump, we just can't see it very well. On the lattice, people normally plot these kind of things to better localize the transition, but also to try to understand how things change when we change the volume. And if this were to be a first order transition or a second order transition or something like that, if we take the susceptibility of the susceptibility enough times, we should eventually find that as we increase the volume, this becomes more peaky and more peaky as the volume grows. But if you rerun at bigger volumes and it stays the same height, then you're not getting non-analytic behavior. And that's what they found. They did a few volumes and they found it was roughly the same height.